Okay, this video is kind of going to talk about functions from x-intercepts in graphs. What I'm trying to accomplish here is our goal is to do the reverse of what we call the zero product property. Remember, the zero product property says that if we have we're trying to factor. So, for example, if we try to factor, let's say we factored this and we made this equal to zero. The zero product property says that, okay, well, if I take this factor and set it equal to zero, and if I take this factor and set it equal to zero, then I need to solve for x. And so my x is going to be 2, and my other x is going to be negative 2. So that's kind of what we're trying to accomplish. But we need to kind of look at these polynomials and kind of do what we call the reverse of the zero product property. So that's kind of what we're trying to do from this. We're trying to take our roots. We're trying to take our roots and actually trying to make a polynomial. So here's an example. Here's kind of like what we are trying to accomplish here. So we have our function, or some polynomial of degree 2, and we set it equal to 0. Remember, this is how you would factor this. This is how you would solve this. You would set the thing to equal to 0, and you would actually go ahead and do your factoring here, and then this will factor, boom, and then you would set the zero product property to both of these, and then you do your solving for x. So this is your what we call the two solutions. So if we were to graph this, at -4 and 2, your graph would look something like that. This is where they would intersect. All right. So let's suppose then, what if we went the other way? And let's say we had, let the x-intercepts be, boom, -3, 4, 1, and 0. Then I want to kind of go backwards to make our polynomial. So remember, we're thinking about that these are equal to that, equal to that, equal to that, and also equal to 0. Then we're going to go backwards. So if we go backwards, we're going to set each of them equal to 0, equal to 0, equal to 0, and equal to 0. Well, that one's pretty straightforward. Then we are going to pretty much, since they're all equal to 0, we can go ahead and set every single one multiplying each other. And once you multiply, you might have to use a little bit of distribution property here, and you will get what we call a polynomial of this degree. Now, what this means is that this right here, after you multiply, you're going to get some a value. Now, the a value is kind of the tippy point of this that says, okay, what does it tell you? Well, it tells you that we have the solutions, but a is kind of like, does it extend it? Does it compress it? That's kind of the thing is, and that's why I made this little note right here. The a, which is in front, can be any value because you can still have your roots. Remember, your roots are your solutions to your function, are the solutions. The a value is just a way to kind of compress it or extend it. And remember, a family of functions is kind of what a is doing. All right, and now we can find what a is if we are given a value. So let's say we wanted to find what a was, and we wanted to plug in 5, 6. Now you would plug in 5, 6. Remember, this is your x, this is your y value at a certain spot. So if you were to come over here, and you would have put in 6 for your f of x, and 5 for x, here, you would actually get a. But that's at a specific point. Okay? So let's try a couple examples. Here's an example here. We have these 4, and we have a degree 4. Obviously, this is just the extra step. We know, because we have 1, 2, 3, 4 roots, that we know it's a degree 4. That's just the extra part. If I didn't give that to you, you can probably do this without that degree. So let's go ahead and do this. So we're going to set them equal to 0, and then we're kind of doing the opposite. So that's kind of what we're doing. Since they're all equal to 0, we can go ahead and go, there's your 4. Now, just to let you know, all these have a 1 right here. Now, what that means is that's what we call that multiplicity. That multiplicity. And what that multiplicity says is that tells me if is there a hit or is there a through, like a cross. This is for your x. And at a specific point, let's put an a value in. Okay, let's keep on going. So you're asking for the polynomial. So you could add more irreducible factors. So what an irreducible factor is, I hope that you understand that x plus, if we had x squared plus 9, this is an irreducible factor. What that means is that you have something what we call complex. You have a complex issue. So that's kind of what's going on. So that complex issue does not really change our graph. These are our intercepts up here. So let's try another one. But this time, let's do something with multiplicity in degree 3. So it looks like we have 1 and we have 2. So 1 and 2. And with a multiplicity of 2. What this means is that since we have our roots here, and you set them equal to 0, kind of do that reverse, now we're going to focus on the multiplicity here. So the multiplicity means that I have x minus 1 to the first power. For this one, I'm going to have x minus 2 squared. Now, if you add your, let's say, exponents, 2 and 1, that makes degree 3. That's what that multiplicity means. If you were to graph this, if the graph would look like this. It would it would be 3, so it's going to kind of go up, and then it's going to kind of go up 2, and just do like a balance. That's what this right here, this multiplicity would do. Since it's even, it's going to be like, oh, it comes down and then it's a bounce off of 2. Okay, so let's do some more examples. So here's a couple of examples. And remember, I don't have to give the degree. So let's do this. So if we take our examples and go, okay, well, this is going to be equal to -2. This is going to be 4. This is going to be 2. And this is going to be 0. Then we just do the opposite. So we got +2 equals 0. We got -4 equals 0. We got -2 equals 0. And then that's just x equals 0. Then since they're all equal to 0, you're going to go ahead and just set them equal to each other. And you can actually put that x in front, make it equal to 0. So all I did is put this over here, make it equal to 0. And if I really wanted to, I can multiply all this out, and my function will be, something like this. It's okay, since we have a 1 degree, 1 degree, 1 degree, 1 degree, we know it's going to be something x to the 4th. And if you want to, you can put a little a, and then it kind of keeps going down. But we can do that later. But we know it's degree 4. Why is it degree 4? Because there's a 1 multiplicity, 2, 3, 4 multiplicity. So there's 4 powers here. Let's try this one. Now, without going through all of these parts here, I mean, we can kind of maybe make this kind of faster if we really wanted to. So I'm going to kind of expedite this a little bit. So there's 1, and then I'm going to make this one opposite. I'm going to make this one opposite, and this one, and that one. I'm hoping that makes sense. I just kind of skipped this step up here. So that means that. Now, since these are all equal to 0, go ahead and apply the zero product property, or the reverse, I should say. And really, you're just multiplying them. Equals to 0. And since these have, let's see, there's a 1, 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 we know that our function is going to be f of x some ax to the fifth, because there's how many degrees? These all have multiplicity of 1. Now, let's dive into a couple of those multiplicities. So let's go to here. Remember, this is going to extend if you keep on multiplying, but we know it's a degree fifth. So let's say I have 2 multiplicity of 1 and 3 multiplicity of 2. So here's how you would write these. You would say, okay, since this is kind of like saying x equals 2, and this is x equals 3. So when you write these out, they should be x minus 2 multiplicity. This is multiplicity 1. And I'm hoping that you remember that this is across the x. Across the x. This one up here is going to go minus 3, but see how it's 2? That's going to be a multiplicity of 2. That means this is a bounce. That means it's a bounce of the x-axis. Now, if you want to kind of go through this, f of x equals, this is going to be ax to the, count the multiplicities, so that's going to be 3. So if you kind of want to look at this, if you kind of make a little graph, and kind of, you can do this later if you really wanted to. Well, at 2, here's 1, here's 2, here's 3. It kind of goes like this. It's going to go through 2. So it kind of goes through and it kind of goes around, bounces, and goes this way. Remember, that's your end behavior of this function. That's your end behavior. That's what the multiplicities do. So if it's even, it does that little bounce off at 3. If it's a 1, it says, oh, I get to go through that. And that's your end behavior. All right, let's try another one, a little bit more. We have 9 multiplicity of 2, 2 multiplicity of 1, and 1 multiplicity of 1. So to kind of hurry this up a little bit, we have x minus 9 multiplicity of 2. We have x minus 2 multiplicity of 1, and x minus 1 multiplicity of 1. And then we start putting this together. You're going to have f of x equals ax. You got 1, you got 2, 3, 4. This is going to be the 4th power. So your end behavior is going to be up and up like this. That's kind of what your graph's looking like if you really want to put a graph. We know our end behavior is both going to go up. And at 9, so let's see, 9's way over here, and maybe we have 1 and 1, so it's going to kind of, this 9, positive 9, is going to kind of bounce off, so it's going to kind of, very easy here. Let's say it kind of hits and bounces off, and then maybe it's going to bounce off, and then it's going to turn, and then it's going to hit 2, and then 1, and go this way. So that's what these are going to do. This is, remember, this is at 2, and this is at 1. So it kind of does this little bounce, comes back around, and stuff like that. And the reason I know that, because I know the degrees 4, and also n minus 1 is what we call the turn, the TP, the turning points. Remember, you're going to go, how many turning points is that you take the degree and you subtract 1. So this should have 3 turning points. So we have 1, 2, and 3. That's kind of what the whole idea of this method is, of this functions from x-intercepts and graphs. So hopefully this helped, and I will see you in the next video.